Because alcohols occur widely, and they are also used extensively as intermediates in synthesis, it's important to know how to make alcohols, and one of the key approaches to making alcohols is reduction. Of the many reducing agents that are available and that act on a variety of functional groups to make alcohols, there are three key reducing agents that I want to focus on. Sodium borohydride, that's two words, NaBH4, lithium aluminum hydride, if you take a look at the composition of these two reducing agents in the periodic table, you'll see very close similarity. And then hydrogen plus a catalyst so we're actually talking about H2 with metals such as platinum, palladium, or nickel. There are others. And right off the bat, we can say a couple of things about these guys. Sodium borohydride is a mild reducing agent and therefore selective. Lithium aluminum hydride, much stronger. Reduces all carbonyl functionality. And then finally, non-selective. For carbonyl. You may recall also reduces carbon-carbon double bonds. Let me illustrate these properties by some specific examples. But before I do that, let me point out one general aspect that's particularly important. In all of these cases, the alcohol that's being made is being made from a carbonyl group. A simple example would be this. But do you know something wrong with what I wrote there? Do you notice that at least it disguises the fact that this makes a pair of enantiomers? And if we're being careful about the products that we write, we really should write one with the OH toward us and the other one with the OH back. And in a case like this, these are enantiomers because there's no other chirality center in the molecule. And there'll be 50-50 mixture. What we call a racemic mixture. So I'm not going to write this stereochemistry out each time I talk about these examples, but I want you to know that when a chirality center is created, and we have no chirality in the starting material, no chirality in the reducing agent, we will get a pair of enantiomers that is a racemic mixture every time. And writing the product without showing its stereochemistry is okay, as long as we remember that really we're making a pair of enantiomers. So let's look at sodium borohydride, lithium aluminum hydride, and hydrogen with the metal catalyst used to make alcohols. Ketones and aldehydes are reduced by sodium borohydride. This will be run in a polar solvent. Examples are ethanol, methanol, or water, depending on the solubility of the starting materials. And in each case, the reduction of a ketone makes a secondary alcohol. While the reduction of an aldehyde using the same conditions makes a primary alcohol. Other carbonyl groups are not reduced using sodium borohydride. So, for example, carboxylic acids, not reduced. Esters, not reduced. So sodium borohydride selectively reduces ketones and aldehydes in very good yields using polar solvents, small alcohols or water to make either secondary alcohols or primary alcohols. Notice that you cannot make a tertiary alcohol this way. Cannot make a tertiary alcohol this way. Lithium aluminum hydride is a much stronger reducing agent and reduces all of these functional groups that are shown here. So in place of the sodium borohydride, we will write lithium aluminum hydride, which is often abbreviated LAH. Now the solvent in this case cannot be a polar solvent because LAH reacts rapidly with these polar solvents, these protic solvents. So it's only in the second step that you actually make the alcohol by adding a source of a proton. These same reducing agents make the same product of sodium borohydride when the substrate is an aldehyde. But unlike sodium borohydride, you can use excess LAH followed by water to make a primary alcohol. And the same is true when esters are treated with excess LAH followed by water. And just as a side note, because there's an alkoxy group here, when we're talking about the LAH reductions of esters, there will be a byproduct which may be a different alcohol. So let me put a prime here to make it clear that this alkyl group is likely to be different from this one, and put a prime here. So the take-home is that aldehydes and ketones are reduced both by sodium borohydride and lithium aluminum hydride, but only LAH reduces acids and esters. And in 3 of these cases, the product is a primary alcohol. Finally, aldehydes and ketones are reduced by using hydrogen in a catalyst, and ketones any of the metals I mentioned, or some others, make secondary alcohols. Aldehydes make primary alcohols. Under these typically mild conditions that are used for these catalytic hydrogenations, acids are not reduced and esters are not reduced. But notice that alkenes are reduced. So if one has a molecule that has both a double bond and a carbonyl group in it, let's pick something like this. Catalytic hydrogenation reduces both the alkene and the carbonyl. While structures like this, carboxylic acids and esters, treated with these conditions, reduce only the alkene. So you see that there's a variety of selectivity that's at play here. If it turns out to be just the carbonyl that you want to reduce, you'll pick a hydride reducing agent. such as sodium borohydride and ethanol. And the product you'll produce is the alkene alcohol. So you can make the saturated alcohol with a hydrogenation. You can make the unsaturated alcohol with a borohydride reducing agent. In a case like this, you could use the lithium aluminum hydride conditions We'll usually write excess to make it clear that we're doing more than one reduction. And in the second step, water. And we'll make the unsaturated structure. That's a primary alcohol. So you could get the saturated ester or the unsaturated alcohol by reducing, starting with the same substrate. These three reducing agents then, sodium borohydride, LAH, and the hydrogen with the metal catalyst, offer a variety of options for selectivity, typically make very good yields, and you can make primary or secondary alcohols, but not tertiary alcohols, using these reduction methodologies. And finally, if you're creating a chirality center from a molecule that had no chirality, you'll make a pair of enantiomers in equal amounts, what we call a racemic mixture.